Welcome to The Explainer. Today, we're diving into one of the biggest mysteries in modern tech, the AI black box. And we're going to see how a really strange branch of mathematics might just hold the key to unlocking it.
You know, artificial intelligence is absolutely everywhere. It's reshaping our world in ways we're only just beginning to understand. But here's the crazy part. We've built these incredibly powerful, almost magical systems. But for the most part, we don't really know why they work. Their internal logic is often a complete mystery, even to the people who build them.
And this whole mystery, it actually has a name. In the field, researchers call it the black box problem.
It's kind of like a magic trick, right? We can feed a bunch of data into one side of the box, and poof, an amazingly accurate answer comes out the other side. But what's happening in between? The billions of tiny calculations happening inside, they're so tangled up, so complex, that trying to trace how a specific decision was made is next to impossible. So to get around this, researchers have been coming at it from two totally different angles.
So the first way is the top-down view. This is like looking at a city from a satellite. You can see the big picture, the overall shape and the flow of traffic. And that's where most research has been focused. But there's this newer bottom-up approach. And this is like walking the city streets, looking at the individual bricks in the buildings, and seeing how they all fit together. And it's this view, from the ground up, that's starting to reveal some absolutely incredible secrets about how these things actually think.
Okay, so let's get into it. Let's do this bottom-up investigation. And believe it or not, it all starts with the tiniest, simplest, most common little piece you can find inside any modern neural network.
We're going to zoom all the way in on this one little component, the ReLU activation function. Now, if you think of a neural network like a brain with billions of neurons, the ReLU function is like the tiny little on or off switch inside every single one of those neurons. It decides if that neuron is going to fire or if it's going to stay quiet. It is the most fundamental piece of the puzzle.
So what does it do? Well, it looks super simple. It just takes an incoming number, z, and if that number is negative, it just outputs 0. It says, nope. If the number is positive, it just passes it along unchanged. But the real secret, the clue we've been looking for, is hidden right there in the middle of that definition, that max operation.
Yeah, that one little function, max. It seems so simple, right? Just picking the biggest of two numbers. But it turns out that's not just a function. It's a key that opens a door to a completely different and honestly a pretty weird mathematical universe.
And where does this door lead? Well, get ready, because we're heading somewhere pretty exotic. We're talking about a field of math called tropical geometry.
I want you to imagine a kind of parallel universe for math. A place where the rules you learned in school for adding and multiplying just don't apply. They've been completely rewritten.
Okay, first up, tropical addition. In this world, when you want to add two numbers, you just pick the bigger one. And right away, that should be ringing a bell, right? Max xy. That is exactly the same operation our little ReLU function was doing.
And the other rule is just as weird. To multiply two numbers in the tropical world, you just do regular old-fashioned addition. Now, with just these two new rules, you can build an entire, brand new kind of algebra.
So let's just pause for a second here. On one hand, we've got this tiny little switch inside an AI neuron. And on the other, we have this super weird abstract branch of pure mathematics. What on earth could these two things have to do with each other?
Well, that's a great question. And for a long time, nobody knew. But then, in 2018, a team of researchers found a connection. And it wasn't just a small one. It was mind-blowing. It wasn't just a loose similarity. The connection was precise. It was perfect. So here it is, the big reveal. They found that a neural network that uses these simple ReLU switches isn't just sort of like an equation from tropical geometry, it is one. The two are mathematically the exact same thing. It's a perfect one-to-one translation.
So what does that mean? It means we can literally translate the entire messy, confusing structure of a neural network into the clear, precise language of geometry. All of a sudden, that black box, it's not so black anymore. We have a way in.
So, okay, we have this new language, this new key. What can we actually do with it? What doors does it really unlock?
Well, it gives us a whole new toolkit. For the very first time, we can look at a network and say, okay, here is the precise mathematical line where it decides cat instead of dog. We can actually measure how complex it is just by counting its geometric regions.
And we can finally prove with mathematical certainty why making networks deeper, not just wider, makes them so much more powerful.
And this image here shows it perfectly. What looks like this totally chaotic, jagged surface that the AI learned, well, through the tropical lens, it becomes this beautiful, structured object called a tropical hypersurface. It's not chaos. It actually has predictable rules. The mystery is being replaced by math.
And this isn't just some isolated idea. It plugs right into other huge questions in AI. You might have heard of the lottery ticket hypothesis. This wild idea that inside every giant AI model, there's a tiny, perfect little network doing all the heavy lifting. Well, if you understand the geometry, you have a much better map for finding those winning tickets.
But this is bigger than just understanding the AI we have now. This is about designing the AI of the future on purpose.
Think about it. This gives us a blueprint. For years, we've been kind of like digital gardeners. We plant some seeds, we water them, and we hope a smart AI grows. But now, we can start to be architects. We can design these things from the ground up, with intention, to make them more efficient, more predictable, and frankly, a whole lot more trustworthy.
So, this connection to tropical geometry has given us the key to the black box. But in doing so, it leaves us with an even bigger, more exciting question. Now that we can actually read the rules of the game, can we finally build an AI perfectly, right from the start?